showed presented. Good afternoon, maybe good morning, everyone. I'm Liangyun Liu from Airspace Information Research Institute. In the next hour, I will give a lecture on mapping land cover and land changes and global 30 meters using time series land center images. There are four contents in my presentation. Firstly, I will give some background about land cover map. And as we know, we have very valuable satellite data such as land center, time series data. We have long-term data records about nearly 50 years. And we have also very high spatial resolution. For land center images, we have 30 meters. And all the time series data are freely shared for all of us. And so if we have the globally time series land center data, can we reconstruct the history of global land cover using long-time series land center stakes? Is my job, also my dream, to reconstruct the history of global land cover in last 50 years. So fine resolution land cover mapping, such as 30 meters and regional or global scale, is regarded as a very important scientific goal, where is usually time-consuming and involves a lot of manual participation. So can we do this job automatically? Can we design automatic software and to reconstruct the long-time series land cover mapping? So I will introduce why time series data are needed for land cover mapping. So maybe we have different definitions about land. For example, surface cover. The land surface cover just means is seasonal variable, is temporarily changed. For example, in summer season, it is grassland because we can observe vegetation cover in summer seasons. But in winter seasons, maybe the land surface are covered by snow. So the surface cover is seasonal product. So if we use only one approach satellite data, we can only give surface cover. The surface cover is seasonal changed. And the second definition related to land is land cover. Land cover just a land property for each year is their annual product. We call the land cover is grassland. Maybe the surface cover is grassland and in summer season, while the surface cover is snow in winter season. Is all land cover. The land cover is grassland. So the third definition related to land is land use. Just this definition is dependent on usage, not natural properties. So it's very hard to map land use because the sensor images just contain information about natural properties. So we need to use time series data for land cover mapping. not surface cover. We can only give land cover mapping use time series data. And after a quicker introduction about the background, I will focus on how can we give automatic land cover mapping use time series data. So the second content is land cover mapping use Spectral based method. I will introduce our method, our algorithm, how to map land cover mapping, land cover. And maybe there are different method approaches for land cover mapping. For example, we just divided into 3 types of land cover mapping algorithm method. First is manual, just means visual interpolation. We can determine each parcel, not pixel. We can determine each parcel use Spectralogy according to texture, color, brightness, and others. So all the knowledge are stored in my mind. We just use visual interpolation. So is a parcel based classification, not pixel based classification. So we know the manual approach is very hardware intensive and time consuming. And the second approach is semi-automatic. The supervised classification is widely used. So we can extract spectral. We can extract spectral features from training samples. For example, we have image. We can select the ground truth, many samples, pixels, and we can use supervised classification to determine other pixels. So all the pixels are determined use spectral features from training samples. And we want to design a new method, a new automatic method for land cover mapping. We call it Spectral-based approaches. Just the original idea is very simple. If we building a spectral library globally, and we can extract spectral features from the spectral library. So if we have an image to be classified, we need to extract the spectral features from the spectral library according to the location and sizes. So we proposed a novel and automatic approach. We called Spatial-Temporal Spectral Library, which aims to produce an land cover mapping with a globe 30 meters. And the details can be shown in a paper just recently publication and ESSD, Earth System Science Data. And if we want to reanalyze a spectral library-based classification, we need and all the satellite images must be quantified. So we need a surface reflex is the base for land cover mapping. So as we know, the reflectance of the surface reflectance observed by models and nanosat is very similar. The spectral response function is seminal. So we can observe that the relation between the surface image of land center and models it tracks well. So we can build in spectral library using models center data to classification land center images. And so the land cover mapping based on spectral library is very similar. It's very simple. Maybe advanced but simple, but very simple. Advanced and simple. Models and land center share the similar spectral bands, and combined with other global land cover products. CCI 2015 has a high classification classifier and is with a more extended classification system and more frequent updated cycle each year. So we can build in spectral library based on the models surface reflex product and also CCI LC 2015 land cover product. We can compare models surface data with ESA CCI LC 2015 land cover products together to extract uniform samples to determine the land cover classes. And we need also do some optimization measures to build in the spectral library. And here's a paper on how do we build in a spectral library and a globally scale. And this presentation gave another presentation about how we building our spectral library, global spectral library. And the global spectral library has been developed using MCD 43A4 surface reflex product and CCI LC 2015 land cover product. And the geographic scale of the spectral library was about 1 degree by 1 degree. And the temporal resolution of our spectral library is 8 days. So we build in a spectral library and exceeding 300 million spectral data in our spectral library. And just means our spectral library also has a spatial resolution, about 1 degree by 1 degree, and a temporal resolution of 8 days. This means that for every land center images, we can extract the local spectral features, and we can also give very close temporary resolution with temporary records and land center data. The temporary difference was within 8 days. So if we have built such a huge spectral library for each geographic cell and any status, we can extract local spectral features for any land cover types. So the land cover classification system just is directly from CCI LC land cover mapping. So we have nearly 30 land cover types in the CCI LC land cover systems. So just here give our speaker labeled based flow chart how to mapping the land cover for each land center scene. For example, we have multi-temporary land center surface luminosity images. And we also have a global spectral label. And for each land scene, we can, for any approaches, we can extract the local spectral features from the spectral label. And we can use this, we can classify the land center images according to the spectral features in the spectral label. And there are many kinds of multi-temporary classification method. And for example, we have different Caesar images. We have many land center images. How can we give a annual land cover map? So to produce annual land cover products, we use time series data. We have two strategies. One is future field strategies, and another is the facial field strategies. The features field strategies is more simple. We just stack multi-temporary spatial bands and vegetation indexes to training the classification model, and then produce the final annual land cover mapping. This strategy is simple and easy to understand, but might lead to crossover dimensionality when the number of training samples is limited. For example, we have 10 approaches. For example, if we have 10 approaches, so for each approaches we have 6 optical bands. 10 approaches we have 60 bands. We can pour all the 60 bands and different approaches together to give a annual land cover mapping. The classification model is based on spectral label. And another feature, another strategy is decision feature strategies. We can train the single data classifier, use corresponding spectral features respectively. Then the second model was used to reweight the output of the single data classifier. It has been demonstrated to have better performance than feature visual strategies. For example, if we have 10 approaches, we can give 10 land surface cover. For example, for approach 1, we can use the land center bands. We can input the 6 optical bands into the classifier, and we can give one approach, give the land surface classification and approach 1, and for approach 2 we can repeat it. So if we have 10 approaches, we can give 10 land surface products. So then we can compare 10 land surface products together to give an annual land cover mapping. So we can use random forest trend to mapping surface cover. Then we can also use use the random forest classifier to view all the 10 land surface land surface classification result to give annual land cover map. So, but we want I will continue with our method. For each land cell or land ground, we can find a spatial and temporal dimension spectral library with a phonological difference less than 4 days. And different from training single level classification, we can use 2-level random forest classifier. And the second level random forest model would use the label soft probability replaced by first level random forest classifier as input. So this model has more robust than single level random forest classifier. So after I introduce how we building the global spectrum library, and also introduce our classification flow chart. So if we have the spectrum library, we have classifier, we have the cluster method. So we need to give a regional or global land cover mapping. We also need to process the land center image data table. So then I will give a quickly introduce how do we build a land center data table. And normally land center data are distributed, are stored by theme. But if we want to give a global land cover mapping, we need to organize the land center image from theme based to share based. So we divided global land surface into about 6 million grids. For each grid, it covers about 0.05 degrees, about 5.5 kilometers. So if we build in the geographical cell, we can pour all the land center images into each geographic cells. So if the land center data are organized, are stored by land center data cube, and the overlaps can provide more temporary observations. So we can combine the spectral-based classification method with our land center data cube. We can quickly give quickly mapping of land cover mapping. For example, on a national scale and also global scale. And here we give an example. Here we give an example of how we produce China land cover mapping. Use spectral library based method and also our land center data cube. And here is our result. We just have about 6,500 land center scenes to cover all the China. And for some geographic grids, we have more than 50 approaches. So we use such land center data cube, input the land center data cube into our spectral library, so we can automatically produce the channel landcard mapping. Here is an example of our automatically mapping result of landcard mapping channel. Just we use test our algorithm, use more than 6,000 land scene to give landcard mapping channel automatically. So this result is very beautiful. Is consistent with our mind which landscape are distributed in China. So we also compared our product with other famous landcard mapping and 30 meters. For example, our Spectral landcard mapping with global landmass 30 from GSC and others, and there is a significant consistency between these three landcard mappings. And however, our proposed method contains more landcard types. And we also investigated the accuracy of our landcard mapping channel. And totally, there are about 10,000 ground points to examine, to calculate the accuracy of our landcard mapping. And we have 9 level 1 landcard types and 19 level 2 landcard types. And for the nominal year and 2015. And here is the result of our landcard mapping. And the overall accuracy is about 80.7%, and the kappa coefficient is 0.757. So if a regional or global landcard mapping can achieve the 18% accuracy, the landcard mapping maybe top level and top accuracy. And then I will introduce how can we give the global landcard mapping, and I will give detailed introduction about the global landcard mapping with fine classification system and 30 meters. So the landcard mapping at global scale is very challenging because we need to handle many challenges. For example, the surface spectral or impervious surface are very complicated, especially for large area impervious surface mapping. It is necessary to classify the global impervious surface and the independent landcard mapping. Just means we firstly mapping impervious surface, then we for other regions, for other areas, we then give other landcard mappings. And our spectral contains both the spectral information and also geographical location. So can this global location information are independently used for landcard mapping? Just means can we use the location of the training samples in our spectral? Can we use the spatial information and also the spectral information? And the landcard mapping on a global scale usually involves huge amounts of computation and storage capabilities. So our solutions are we need the incorporation of mountain source and mountain temporal luminescence imagery is used to mapping and global impervious surface with Google Earth NGL platform. And the global landcard mapping strategy can be divided into two ways. Use mountain temporal classification based on spectral, neighbor, and non-centered cable. We can also use the feature classification method based on multi-temporal non-centered image with GE platform. And the ground trend samples are from our spatial library, because our spatial library, there are more than 300 million training samples. For each training samples, we have location and spectral information. So when we do the global landcard mapping firstly for impervious surface mapping, and we found that the microwave data, SAR data, are important for accurate landcard mapping. And if we compare the microwave data together, the mapping accuracy can be greatly improved. So firstly, we need mapping global 30 meter impervious surface land cover. Although the independent optical imagery have been successfully employed for regional or global impervious mapping, accurate estimation of impervious surface remains a challenge due to the diversity of overall land covers, leading to difficulties of separating different land covers with similar spectral signatures. And the optical imagery only captures the surface reflectors characteristics, where the SAR images called provide the structure and diagonal tracker properties of the surface materials. So the incorporation of mountain source and mountain temporal luminescence data have been demonstrated to improve the impervious mapping accuracy. Here is our flow chart, and for global impervious mapping, surface mapping, we need nighttime imagery from DMSP OLS nighttime imageries, and we also need DM data, and we also compile the spectral features. We use spectral features in 15 percentile, and spectral features in 85 percentile spectral features. And also we need textual features. So the spectral features and text features are compiled together, and for global impervious surface mapping. And to give a global impervious surface mapping, we need huge optic data and also SAR data. So we used about 420,000 scenes nanocenter OI images. We also use 85,000 scenes Sentinel-1 SAR images. So we have almost more than 1 billion. More than 5,000 nanosat and Sentinel-1 SAR images together to give one global impervious surface mapping. And we introduced before, we have more than 300 million training samples. So the training samples are huge and are enough for supervised classification of our to mapping impervious surface. And here is our result of the global flancation of impervious cover derived from multi-source and multi-temporary nanosat 8 surface reflectors and Sentinel-1 SAR images acquired in 2015 and 2018 or 2016. We can observe the impervious cover are denser and in East China, Europe, and also America. And here give a quick example of our impervious radars. Can capture the cities, Beijing cities, Tianjin cities, and also some villages and some roads very clearly. And we also investigated the accuracy of our 30-meter impervious surface. And the accuracy is also compared to other 5 famous impervious surface products. So together, the accuracy of 6 sets of 30-meter impervious surface products was verified using 15 typical test areas. These test areas are randomly selected in the world. Totally, there are 11,000 ground truth points. The result shows that our result gave the highest accuracy performance, with overall accuracy about 95%. Is significantly higher than other products. And we have a globally spectral library. We also have a globally nanosat Geographical, and Geographical including nanosat images and also Sentinel-1 SAR images. So after we gave the impervious surface products, then we mapping other landcover types. And here give a result of our global 30-meter landcover mappings and 2015. And from the global landcover mapping result, and from the visual judgment, the landcover mapping is good. And snow cover, desert cover, and the boreal forest cover, and also desert, and is consistent with our traditional geographic knowledges. And we also need examine the classification accuracy of our result. So globally, we collected about 46,000 validation samples globally. So we use 46,000 validation samples to investigate our classification accuracy. And here is give a result of our global land cover mapping with the fine classification and 30 meters and 2015. And the overall accuracy is 18.2% with a kappa coefficient of 0.784. And details about our GLC FCS 30 can be available and on recently paper 2001 just published and also system science data. And we also examined we also compared our GLC FCS 30 with other famous global land cover products. And here give a zoom-in maps of 6 regions: Northeast USA and Midwest USA and East Australia and also East Europe and Northeast China, North China. And for example, here is Northeast China. And the classification information is give very detailed and rich for spatial information, rich for spatial details, and the forestry is the classification result is very beautiful. And here just give our land cover mapping and Australia. And here is clearly show where is the cropland distributed in Australia, Western Australia and East South Australia, and the wetland distribution and shrub distribution, desert distribution, and forest distribution. And the land cover mapping is very beautiful. You can see the picture with brains how our land cover mapping looks like. And our global land cover mapping also can give very local information. For example, the land cover mapping in Beijing City in 2015. And here give another example of how our land cover mapping perform in West Australia. Here, this color just means cropland, but we can observe very clear border. What's the border? For example, Australia, here is the revisited, convisited regions. So the land cover types are very wild. But for cropland areas is cropland. So here give some very clear information. Our land cover mapping can give very continuous result and also give very clear border of different landscapes. And here is a real color images of West Australia, why and such area is quite different with cropland. And our land cover mapping can capture such true land cover distributions. For example, this border is very clear in our classification result. And this border is also very clear in our classification result. And we also compared our global products with other popular land cover products. For example, with our global land cover mapping with a fine classification system 30 meters, GLC FCS 30, and from GLC and global under 30, and we can observe that all GLC FCS give best accuracy, give the most accurate mapping of global and count mapping. And also, there are some other scientists examine and compare our result with other results in different regions. We just gave examples. A paper published on luminescence just compare the consistency of luminescence and products in the tropical forest climate regions, a case study of in Indonesia. Because the research of high accuracy landcount classification in tropical forest area is very challenging. And the result of the third-party nationwide inspection in Indonesia shows that GLC FCS not only has a fine classification system, but also has a high overall classification accuracy, which is better than other two famous landcount mapping. And we have another 10 million for introduction about how can we updating global and cover use time series landscape images. So we have for example landscape images from 1930 meters from 1984 to 2020. So can we reconstruct the landcount mapping in last 34 years? So we can also use our algorithm, use our classifier training in 2015, apply the classifier algorithm in other approaches to reconstruct the global landcount mapping. However, most of the studies updated the global landcount mapping by independently classify the images of the target years. However, such independent classification strategy will lead to a large number of inconsistent classification results between landcount mappings in different periods, and thus introduce a large number of procedural changes, false changes in registers related to analyze temporary and spatial changes. For example, the global cover products claimed that the global cover products cannot be used for any changed detection applications, not even for directly comparison with the previous global cover 15 products. We have global cover products under 2009, 2005, but we cannot calculate we cannot use such two approaches to detect the landcount changes, because the classification system is very limited. The classification accuracy is about is only 80%. The landcover changes proportion is very small, is much smaller compared with the classification accuracy. The accuracy is very low. The landcover changes proportion is very small. How can we address this problem? So there are many kinds of mounting period non-cover mapping. For example, NLCD national non-cover dataset by USGS uses dual period change detections algorithm, and in order to improve the consistency between the non-cover products of each period, NLCD began to update products based on dual period change detection method. Just means if the pixels is stable, no changes, we didn't classify these pixels. We only label pixels, update pixels for changed pixels. Unchanged pixels, the non-cover types remain stable, remain same. We only update non-cover labels for changed pixels. Firstly, we need to detect the changed pixels. So just means the change detection is very, very important for mounting period non-cover mapping. And a very young and also distinguished scientist, Professor Zhu and Carnegie Gale University, and they claimed that dual period change detection algorithms are relatively simple to implement, and many change detection algorithms use fine resolution images, have used two days of remote sensor images. However, because the spectral features are extremely complicated, and the quality of image is affected by many factors. So if only the spectral signatures between two periods are compared, the change detection accuracy is very limited. And so we need to design a new method to improve the change detection accuracies. So Professor Zhu designed a very famous change detection algorithm called CCDC detection algorithm. And the change detection based on time series images can mitigate the false changes caused by errors in the dual period change detection processes. And for example, we can model the valuation of the non-surface reflectors. For example, for such valuations, we can observe that the forest is growing. No non-cover types changed. But for such curves, time series curves, we can observe a rapid, we can observe a non-cover. We can observe a changed non-cover types, non-cover in this period. So we can use time series method to detect the changes. So if the pixels are changed, we can update the pixels non-cover types. If the pixels are stable, no changes, the non-cover types is same as before. So we only update the changed pixels. So we designed a non-cover updating method based on continuous change detection algorithm. Here give an example of our the performance of our continuous land cover mapping from 2001 to 2020. Last 20 years in Beijing cities, and for the stable regions, the land cover types are same in last 20 years. But for example, the Liangyun Lake, we can observe the water area increasing in last 20 years. We can also observe when the capital airport are building in Chaoyang district and also in Daxing district, and a new airport building in last in about 2018. We can observe another large airport building in South Beijing. So the continuous land cover mapping it can give very reliable land cover mapping for change analysis. We can use such land cover products to calculate how the land cover mappings are changed in last 20 years in Beijing. But globally, such algorithm is very, very time consuming. So we can use such a method to detect the land cover changes for stable pixels. The land cover types are remain stable. We didn't classify such pixels. We only use a continuous detection method to determine the changed pixels. The changed pixels are reconfined and updated. And here give an example of a new method for continuous change detection and mapping updated based on reference land cover mappings. We didn't give annual land cover mappings. We just gave land cover mapping for each 5 years. The temporary interval is 5 years. So we tested our result in 2009, gave a GLCFCS setting and 2009. Then we applied our algorithm globally in the GLC and global land cover mapping and 2000 and for each 5 years we updated our land cover mappings. Here just show the expansion of impervious land cover surface in Beijing, Tianjin, and Hebei province in last 20 years, and the expansion of impervious surface in Pearl River Delta and also Yangtze River Delta, and this region is the water factory. We can observe a huge land cover mapping change, and also we can give global land cover mapping in 2020. So our result can reconstruct the history in last 25 years globally. And here they give a global impervious surface mapping over last 35 years, and we can give 80 epochs land cover mappings in last 35 years in Beijing and also globally, and we can observe, we can calculate the increase of impervious surface over last 35 years in China, and also give the cropland increase in last 35 years, and we can observe that more than 1 million kilometers inclination over land globally. 1 million land, 1 million square meters in last 35 years, especially and Africa and also South America. And also we can observe the huge inclination of impervious surface in last 35 years globally. The area of impervious surface is nearly doubled. Is already doubled. And you can, if you want more details, you can download our papers. And the global land cover mapping products are available for 2020 and 2015, and will be freely available in August 2021. In next month, we will open our global land cover products with fine classification system from 1985 to 2015 will be available soon. So thank you for your attention. There is still a long way to go, a long way forward for land cover mapping globally. Thank you.
Okay, thank you very much to Professor Liu. Thank you. And Professor, there's some questions from our trainees in journal. The first question is, what is the main difference between MODIS and Landsat data? You can check it in the journal text box.
There is still difference between the surface reflex between MODIS and Landsat data. So we need to normalize the difference. So we need to use MODIS as a reference, and to use MODIS reflex data and the reference to normalize the Landsat images.
Okay, thank you. The next question is, how can we extract uniform samples for two different types of data?
Oh yes, yeah. And the uniform, we only extract uniform pieces from MODIS data and global cover 2015 and cover products. We need to define what is uniform pieces. Just means the spectral variation of the neighbor pieces are very, very small. The difference, the spatial difference between the neighbor pieces are very, very small for reflectors, and also the land cover types are same for neighbor pieces in the land cover products.
Okay, thank you. And students, it's so warm. So there's some questions follows. Next one is, if we find out land cover change of 14 years of forest and build-up area, the image of 1980 have low resolution. Well, now for 2020, there are high resolution images. How much will be occurred if we find out the change of 14 years?
We only mapping the global land cover mapping and 30 meters. Just means we just use only Landsat 5, Landsat 7, and Landsat 8. We didn't use MSS satellite because the resolution is different. So we only reconstruct the historical land cover mapping in last 35 years. So if we want to reconstruct the last 50 years history, we need to use non-center MS data. These are next steps.
Okay, thank you. And go on. The next question is, up to which we can follow this approach to get acceptable accuracy? What determines the level to decide up to which level?
Sorry, I didn't.
I see the text, the sentence says, up to which we can follow this approach to get acceptable accuracy. What determines the level? What determines the level?
What determines the level?
And maybe I guess the him is the factors to the accuracy level, maybe.
Oh yeah. The classification system, the classification accuracy is very challenges. So far, if a global land cover radar can give 18% is top level accuracy. It just means it's very hard to achieve accuracy higher than 18%.
Okay, thank you. There's more. Next question is, how to calculate the kappa coefficient? That means the accuracy of RULC.
Oh yeah, and and there are many software and there are many details in the you can find numerous references to tell you how to calculate the kappa coefficient.
Okay, and the last one is there any remote sensing systems to land elevation change due to sediment?
Is any remote system to land
elevation?
Oh yeah.
Due to sediment.
I don't know. I know what he said. If we want to monitor the land elevation, we need to use 3-dimensional photo. How to say? We need to use such as LiDAR and other methods to mapping the elevation of land surface.
Okay, thank you.
Yeah.
Okay. Is there any more questions? Let me see. There's a question. It means which time period of satellite image can be best for the land cover classification?
Oh yeah, I guess you want to know which season is better for land cover mapping. And in our classification algorithm, we use all the image available. We pull all the land center images together for land cover mapping. Just means the classification algorithm is time series classification, so not a single data classification. So if we have only very limited approaches, maybe the sum season is better for land cover mapping.
Okay, thank you. And the final one question is how to download the global Sentinel data. Is how to download the global Sentinel data. He has
global which data?
Sentinel shopping.
Oh, Sentinel data, yeah. And we didn't download any non-standard data. We just use all the non-standard data and Sentinel-1 data in GE platform. And you can visit, you can use Sentinel-1 data in Google's Angel platform freely.
Okay. Thank you very much. I say our trainees answer some questions to each other. That's very good. Thank you very much for participating. Okay.
Thank you.
Thank you.
Thank you.
Thank you, Professor Liu. No, thank you very much.